All right, let's talk about a programming concept that honestly feels a little bit like a magic trick. It's called recursion, and it's this idea of a function that calls itself. I know, it sounds like a riddle, right? But stick with me, because by the end of this, you're going to see it's one of the most elegant, most powerful ways to solve some really tricky problems.
So here's the game plan. First, we're going to wrap our heads around the core idea, like what even is recursion? Then, we'll get our hands dirty with a classic example, the factorial function to make it all real. After that, we got to talk about the one rule, the one unbreakable rule of recursion. From there, we'll see how this idea goes way beyond just numbers, and finally, we'll pull it all together into what I like to call the recursive mindset.
Okay, section 1, the big idea. At its heart, recursion asks this totally fascinating, kind of mind-bending question. What if a procedure could call itself to get its work done? What if it could define itself using a smaller, simpler version of, well, itself?
Let me put that another way. Think about it like this. What if the big problem you're trying to solve actually contains a smaller, identical copy of the exact same problem inside of it? If that's true, then maybe, just maybe, the solution can also contain a smaller version of itself. And that right there, that's the key insight that makes recursion so incredibly powerful. So, to put a formal definition on it, recursion is just a process where a function is defined in terms of a simpler version of itself. And, this idea isn't new. It's actually borrowed straight from mathematics, where they call it an inductive definition. You start with one simple, undeniable truth, and then you build everything else up from there, one step at a time.
Now, for this whole thing to work without, running forever, every single recursive function needs two essential ingredients. First, you've got your base case. This is the absolute simplest version of the problem, the one where you just know the answer directly. You can think of it like an anchor or an emergency brake. It's the stopping condition. Then you have the inductive step. This is the part that does the work. It breaks the problem down and makes that recursive call, inching you just a little bit closer to hitting that base case.
All right, that's enough theory for now. Let's make this abstract idea totally concrete. We are going to walk through probably the most famous example of recursion you'll ever see, calculating a factorial.
So, what is a factorial? You write it as n with an exclamation mark, and it's just the product of all the positive whole numbers up to n. But look closely at the structure. 6 factorial is really just 6 times 5 factorial, and 5 factorial is just 5 times 4 factorial, and so on. See that? It's literally defining itself in terms of a simpler version of itself. Oh, and by the way, remember this little fact? It's going to be super important. By mathematical rule, the factorial of 0 is 1.
And check out how beautifully that idea turns into code. It's so clean. Our two ingredients are right there in plain sight. That if n equals 0 part, that's our base case. That's our anchor. The else part, that's our inductive step. It returns n times the result of calling the very same function on a slightly smaller number, n minus 1. Okay, so how does a computer actually process this? Let's trace it. Let's pretend we're the computer and we're calculating the factorial of 3. First, factorial of 3 starts running. It gets to the else block and realizes it needs the answer to factorial of 2 before it can finish. So the entire factorial of 3 calculation just pauses. It hangs in limbo, waiting. So then factorial of 2 kicks off. It needs the answer to factorial of 1. So it pauses. Then factorial of 1 starts, sees it needs factorial of 0, and it pauses too. Finally, factorial of 0 gets called, and boom, it hits our base case and immediately returns the value 1. No more calls, no more pauses. And this is where the magic really happens. As soon as that base case returns a value, it's like a chain reaction in reverse. The paused factorial of 1 call suddenly wakes up. It gets the 1 it was waiting for, calculates 1 times 1, and returns its own result. Then, the factorial of 2 call that was paused wakes up, gets the value it needed, calculates 2 times 1, and returns 2. And finally, our original call, factorial of 3, wakes up, gets the 2 it's been waiting for this whole time, calculates 3 times 2, and returns the final answer, 6. It all unwinds perfectly. Now that whole beautiful chain of events only works because it eventually stops. That base case isn't just a friendly suggestion, it is the one unbreakable rule of recursion. So, what happens if we break it?
This is it. This is the single biggest trap you can fall into with recursion. If you forget to define a base case, or, and this is more subtle, if your recursive step doesn't actually move you towards that base case, you create a monster, a problem with no end.
For example, what if we tried to use our function to get the factorial of a negative number? Well, factorial of -1 would call factorial of -2, and that would call factorial of -3. You see the problem here, right? The number is getting smaller, but it's moving away from our base case, which is 0. It will never, ever hit it. You've just created an endless loop that, on a real machine, will keep going until your program completely runs out of memory and crashes.
And that leads us to this crucial takeaway. You have to be incredibly careful. You must guarantee that every single possible path your function can take will eventually lead to a base case. That's the fundamental contract of recursion. If you break it, the whole elegant system just falls apart.
Okay, so you might be thinking, this is a pretty clever trick for math problems. But the real beauty of recursion is that this pattern of thinking applies to all sorts of things, not just numbers. Let's see how the exact same logic works with something like a list.
The logic is a perfect parallel. With numbers, our inductive step was to break n down into n and n-1. With a list, we can do the same thing. We can break it down into its very first item and then everything else, or the rest of the list. That rest of the list is just a smaller, simpler version of the same kind of problem. And our base case? Well, what's the simplest list you can imagine? An empty one.
So let's use that idea to add up all the numbers in a list. Here's the code. Our base case, if the list is empty, the sum is obviously 0. Easy. Our inductive step, if it's not empty, just take the first number and add it to the sum of the rest of the list. It's the exact same pattern we saw with factorial, just applied to a different type of data. And just look how elegant that is. No temporary variables, no for loops.
Let's really drive this home by looking at a more complex task, like sorting a list. The typical iterative approach on the left, it builds up a sorted list piece by piece inside a loop. But the recursive version on the right thinks about the problem completely differently. It says, look, I don't know how to sort this whole big list, but I'm going to trust that I can magically sort the rest of it. And if I can do that, then all I have to figure out is how to insert this one first element into that already sorted smaller list. It's a profound shift in how you approach the problem.
So we've seen what recursion is, how it works, how it can break. Let's pull all this together. Let's actually define what it means to have a recursive mindset.
So what's the secret sauce? First, you always find your anchor, that simple base case that stops the whole process. Second, you make absolutely sure that every recursive step you take moves you closer to that anchor. But third, and honestly this is the real magic trick, you have to take what's called a recursive leap of faith. You have to trust that your function will just work on the smaller problem. Don't try to trace it all the way down in your head. Just trust that sort rest of the list is going to give you back a sorted list, and focus only on your one job, what to do with that result. That leap of faith is everything.
In the end, recursion isn't just a coding technique. It's a way of seeing the world. It's the art of looking at a huge, intimidating problem and realizing that it's actually just a very simple step applied over and over to a smaller and smaller version of itself until you finally hit rock bottom.
And that's our deep dive into recursion. But I want to leave you with one final thought. This pattern of self-similarity, it's not just in our code, it is everywhere. You can see it in the branches of a tree, in the jagged shape of a coastline, in the delicate structure of a snowflake. So, now that you know how to spot the pattern, my question to you is, where else are you going to start seeing it? Thanks for watching.